our coding lecture. So last time we learned several like Pythonic basics that is needed for us to understand, let's say, so how the thing's going to be working for PyTorch if we want to implement our own optimizer. So let's run the code till this point. Okay. Wait. Still small, I don't know why, but okay, let's run the code to this point. So we just click run before. Oh. Oh yeah. So we have some errors. Okay. So that's from manual. Okay, so here is where we were last time. So what happens here is, so for example, if we want to train a model, for example, so this is a famous MNIST data set. So MNIST data set is handwritten digit. You guys see in the so you guys already saw this back in homework, coding homework too. I mean, this is perhaps the most famous data set, okay? Or can I use this? So this is the most famous data set in machine learning, and basically so as we can see here, if we use PyTorch formalism, so if we use this PyTorch formalism, so this is the MNIST dataset we just loaded. We use a formalism called data loader, so it gets everything done for us. And this is the class data loader, and we can change this data loader to an iterator, which means we can call next function. So next to the function on this thing. So basically, what happens is it gives us a bunch of samples that has the size of. So this is a tensor size. Okay. So in batch means we have 64 samples in the batch, and in channel is how many channels in our image. So for a regular image we have, normally it's 3 channels RGB. Okay, sometimes we have 4 channels CMYK, but most likely, so we'll have this 3 channels, so red, red, blue, and this is the dimension of each tensor or image, whatever. So this each image is 28 by 28. I really want to make this bigger, but yeah, I try. Okay, so 15 point. Oh, cannot change. Oh, your browser is managed by organization. I cannot change this font. Yeah, I think it's better. It's better. Okay. Oh yeah, it's better. Yeah. So So for example, so sample is a list. Okay, so let's print type of sample. So each batch is a list, so it has two entries. Okay, so sample, the first entry is the image. So it's a batch of images, and the second entry of sample is the corresponding label corresponding to the image. So for example, let's try to visualize. Okay. So do we have maps on this? No, we don't. So for example, if we view PLD image show sample. So for example, this is, for example, if we want to show the first sample, okay. So this is sample 0 is a batch. Gives a batch of images, and this returns the first image. So this gives us so basically sample 0 is something like this, okay. It gives us a 1 by 28 by 28. So most likely this will give us error, or it shows all white because we didn't specify the channel. Let's try it. Okay, not list indices must be. Oh, I see. Sorry. My bad. Okay. So this is already a tensor. So this gives the tensor of a batch of images. So what we want to do is we do this. So return the first image. So this most likely will be, all white. Okay. So because, because this is invalid for image data. So what we can do is, so we have it now, right? So if we search Stack Overflow, so I suggest everyone do this if we see an error. Okay. So, but how to fix this is we get rid of this one. We get rid of this one dimension here. How we can do this is we simply call a simple function called squeeze. All right. So if we call this, we'll get an image. All right. So we get this 28 by 28. So this is number 5. Okay. I mean I don't know how you write number 5, but looks like an S, but this is number 5, and as we can see, it corresponds to the first sample here. Okay, so if we change to the second, we'll get 0. All right, so which corresponds to 0 here. So let me delete this cell and move this to the top. So sometimes you can import SQL as well. I like this package SQL. Okay, so this is how we use it. And okay, so let's back here. And so for example, so this will give us 0. And let me see if there is a.
There's no blind.
Okay. So everyone can see it, right? Okay, thank you. So this is 0, and I mean we can do similar things. For example, so we see this is 4. So this is 0. This is index 0, index 1, 2, 3, 4. So index 4 is the 5th entry. So let's try it. Okay. So we'll see. This is 9. So what happens is basically it gives us a batch of images. So basically, I don't know, machine learning 101. And so in our final project, we'll handle a much more interesting data set. So it's Japanese characters, but anyway, so as we can see, so this gives us samples. So here is we want to build a neural network to tell what digit is this. Okay, so for example, we give this tensor to a neural network. This neural network tells us, oh, this is 9. Okay. So this is the idea. And this is how we do it. So let's so this is a typical template class for neural network. So let's learn one by one. Okay. Yeah. Let me remove this typing thing just to make things less confused. Okay. So remember, we had a class, right? But we didn't have anything after the class name. So let's back here. So we have class definition, and then this class is called vector, and then it's comma. Okay. So sometimes it has this syntax as well. So, or you guys will see something like this. Okay, or you will see something like this, which is object. So if you type object here, it will change color. So for example, object. So it's a different color than the vanilla, this black color. Okay. So this will do as well, but this was a Python 2 tradition. Okay, so what does the parentheses after that mean? Is it's a subclass. All right. So what does subclass mean is so it's a subclass. It has inheritance. Okay. So subclass means the inheritance. Every method of NM module. So NM module is the most powerful module of this neural network interface. I mean, it doesn't have to be a neural network, you know. So I even wrote my, fluid dynamics solver using NM module, like how to solve Navier-Stokes equations. Okay, so NM module is a extremely powerful, Facebook implemented this module. So it inherits everything from NM module after calling the super function. Okay, so let's see what happens. So first, this is initialized. So for example, so this is called constructor. So this is a constructor method. So once we call the init method, initialization, and then we call the self, and this is parameters, we give this function. So it's pretty much like a regular function expression, except the first variable has to be self. Okay. Okay, now once we call this function, this is a super, okay. So this is super, but this is Python 2 tradition. So in Python 3, you can delete this, it still works. So let's do this. This is simpler. So Python 2, try to make it formal and introduce some syntax that can be avoidable. But okay, so if we call this function super and dot, okay. So basically, this initiates its like mother class. So this is like a subclass. This is like the parent class. Okay. So NN module is a parent class. Oh, yeah, I forgot. Why every time I have to change this? I don't know. Okay, here we go, much better. So, okay, so what happens is if we call this dot, so this super parentheses basically calls its parent class NN module. And it initializes, so right now there is no parameters in it, but it inherits every method from the NN module. So later we'll see, we can add something here, super init. Okay. So this self, this is like initialization. It doesn't have any return. So this function, so the constructor doesn't have any return value. All right. So it returns none. All right. So what happens is that to build this object, for example, so self dot linear 0 means we have a linear 0. So we have this NN linear. So so what happens is, come on. No, it won't. Okay. So what happens is, okay, so this is a help. Oh, it won't render LaTeX. I see. But anyway, so this is basically linear transformation to the incoming data. So you see here. Okay. I forgot where my marker. Yeah. Anyway, so okay, so this is the input size, and this is a linear transformation. So if we have a vector, but later we will see. Okay, so later we will test each line, and then we have an activation. So all of these are built-in functions. We don't have to implement ourselves. We only have to implement some optimizer. So we don't have to implement the neural network, and lastly, its self-linear 1 is from 256 to dimension 10. So the first entry of linear is the input dimension. Okay, so input dim and output dim. So it's basically a linear transformation, so as indicated by the help. Okay. So applies a linear transformation to the incoming data. This is basically what it does. Okay. And then the other core method is called forward. Okay. So and again, the first entry of the input should be self, and then this is like the input tensor. Okay. So this method is by default user has to implement. So if a user want to implement a neural network, we have to implement the forward method. Okay. So this we first get rid of the color channel. We'll see what happens. Okay. And then we put it. Okay. So then we put this, image tensor into the first linear transformation. So this is x1. So we apply a linear transformation on x, we get x1. And then we apply the activation function on x1, we get a1. And then we apply the linear 1 on a1, we get output. And the return is output. So, and all these functions, self dot linear, is defined in the constructor. Okay, so in order to call a function, So using the syntax self-dot something, we have to define them in the constructor. Okay? So let's run this. Okay. So here is how we dissect this neural network. So right now, I mean, on the market there are perhaps I don't know, millions of models on GitHub. So how do we perform our research? For example, if we want to design a new neural network based on the existing ones, how do we do? The first thing we want to do is we do an explicit forward. So this is the most basic one, but you can also use TensorBoard. Something called TensorBoard. Okay. But this is how I normally teach students to do things. That is, we try, okay. So basically we try an explicit. So this is wrapped. So what we call, so in programming is, there is something called wrapper. Wrapper is basically a function. Is we wrap this whole routine. So this has basically 4 lines of code, right? I mean, we can explicitly run them without any function, without any return, okay? But we can also wrap it in the function, so it has this function definition, input variables, and the return value. But we can also explicitly run it, okay? So like this. So for example, so let's run these. And what happens is, it runs this code, okay? But without the self, all right? But without this self reference to this class. So what happens is, let's run it. So yeah, I should break this into, I forgot the keyboard shortcut. So let's see, split. Where is split? Split at cursor. Oh, so it's different. Okay. Okay, let's try this. Is it working? Oh yeah, it's working. Okay. Okay, so this is our first line. So this is the data we want to input into the model. Okay, so it has 64 images. It has a single channel. Single channel just means it's a grayscale image. Okay, so I mean the brightest pixel is white, and the darkest pixel represents this black color, and so it's basically from 0 to 255 for our case, and so now let's look at the first line of the neural network. Okay, what is this? All right. All right. So actually, this does 2 things. Not only to remove color channel and also flatten the tensor. Okay. So x is this size, right? So x size 0, let's look at this. So x size 0 is 64, okay? So x view, and this is the batch size. This -1 is we let PyTorch figure out what this dimension should be, okay? And then we'll get 78. Okay? So for example, so the first dimension is the batch size, which is 64, and then, okay, once we remove the rest dimension, so the rest dimension is like a 3D tensor, but we can also always flatten it. So it's like, imagine this is a 28 by 28 matrix, okay? We just write its entry one by one. like we write its first row. Sorry, first row, okay. And then when we write its second row, we don't do like second row anymore. We just write the second row after the first row. So it becomes like sequentially a sequence. Okay, so this operation is called flatten. So let's see an example. So for example, we know that so array equals torch a range. So for example, 9. Let's do view 3 by 3. Okay. So let's print this ARR. So we get this, right? But we can also flatten it. So let's print ARR flatten. So there are two ways to flatten it. We can always do view -1 or 1 minus 1. Okay. Or we can do this flatten, which is a built-in function. Okay. So there is a slightly different. Flatten gives us only one dimension, but this is a 1 by 8, 1 by 9, like so 1 row and 9 columns. Okay. So this is what happens here. So basically we have the batch size. So the shape is now the shape becomes batch size, which is 64, and then this is the input dimension. Okay, so this is the input dimension of our neural network is 784. So what is simple? Then let's look at the next. Okay. So the input size. So then this is our input size. So for example, so we have, this is our last dimension size, which is our input size. So this is size -1 basically gets us this 784. So for example, the nicest thing about Python indexing versus some anti-human indexing like in C++ or MATLAB is Python has negative indexing. Okay, so the 0 always returns the first entry, and we can always use negative to get, for example, -1 is the last entry, -2 is this. So the good thing about this is when we subtract, it automatically cyclic. I don't know if you encounter this programming difficulty in MATLAB, is because when we want to retrieve something that is cyclic, okay, for example, we want to run, yeah, I didn't bring my marker, I should have bring my marker. But anyway, so.
I have markers.
Thank you so much. Yeah. Remember to remind me to pay you. Okay. So we encounter this in programming question. That is, so I is indexed. Okay. What happens is, so in 1, 2, 3. So this problem. Okay. All right. So for example, what happens is, what we want to do is this array's first entry is 1, second entry is 2, third entry is 3, right? But now, what happens is we want to compute, okay? Let's say we compute something like this. Let me turn on the light. Okay. Yeah, I only need one, but this is already very illustrative. Okay. All right. Think about this. So we have an array. We have like this type of formula. It's x sub I subtract x sub I minus 1. Okay. So when I is 1, this is x sub sub 1, subtract 1, subtract 1. Okay, so let me try to use this again. But there is no 0, as we can see. So this is 1. So when I is 1, this is x1 subtract x0, but there is no x0. Okay.
So we cannot use any backward.
Yeah, we cannot do any backward, but okay. So if we have 3 entry and we want to compute its difference using this subtract this. Okay. So that's why indexing starts from 0 and negative indexing is awesome, is because when I is 0, this is xi, which is x0. Okay, so we have basically, so this is x1, x2, x3. Yeah, so I think back in before the financial crisis, I was interviewed at Wall Street, but then I didn't get the job because the financial crisis. Anyway, so so this was the interview question actually. So why Python has negative indexing? But this is already, it's in the interview question bank online. So why it has negative indexing is, this is very handy. So this is one example, but there are other nicest thing about negative indexing. Okay. So when I is 0, okay, x0 subtract I is 0, x minus 1. X minus 1 is this guy. We compute the difference between these two. Okay. But if we have this, starts from 1, x0. So we have to introduce an extra here. Okay. So calling this x0 is counterintuitive. Okay. But calling this x of minus 1 is very, I would say, intuitive. Okay. So introducing negative index and the index starts from 0 solve this problem very elegantly. But in MATLAB we have to create a cyclic tensor. I would say it's not very nice. Thank you. Okay. So this minus 1 gives us 784. And so for example, this is 784. So this is the input dimension. Okay. So this is also the input dimension. So this is also the input dimension of a neural network. So this is all right. So this is our first layer. So for example. So how I came up with this code is, let's look back at this code. Okay, so this is how the PyTorch neural network formalism is. So this is self-linear 0. But where is this defined? The self-linear 0 is defined here. So how we do is we get rid of the self. We just extract this code. We let linear 0 be this guy. And then we call linear 0 afterward. So this is like the explicit forward. Okay? So for example, so this is 784, 256. Okay? We perform a linear transformation on this tensor. What happens is, so this tensor is 64 by 784. Okay? And once we perform this linear transformation, its last dimension gets changed to 256. So let's try it. Okay? So this is our like the input before the first layer. It's 64 by 784. So a linear transformation transforms the last dimension to the number we set here. Okay? All right? So the dimension, so this dimension, like I wrote in the comment, so this dimension should never change in our forward. Okay? So we would always keep this 64 dimension unchanged, and then let's try this activation. So activation actually doesn't change. So print A1 size. So this activation actually doesn't change the shape of the tensor from previous layer, but what it does is it removes all the negative entries. Okay, so let's try to do this. So for example, so this x1 mean, okay. So this n ReLU function, it's the same. It's the same like trick we use. So we basically remove the self. We just let activation to be this guy, and then we call the activation directly without the self. So so this is what we have, and as we can see, this is A1 size. It's the same, 64 by 256. Okay. And it doesn't change the size, but as we can see, originally the minimum is a negative number, but after the ReLU function, so its minimum becomes 0. So, come on. Okay. So this is basically ReLU is x plus. It's a maximum of 0 and x. So which means if x is less than 0, it gives us 0. Sorry. X is strictly less than 0, it gives us 0. Okay. So now let's next. So this is our last layer. Our last layer is transforms 256 to 10. What does 10 mean? 10 basically means 10 means the number of classes. So in this case, it is we have 10 types of digits from 0 to 9. Okay. So if we have 10 classes, if we have 100 classes, this 10 should be 100. All right. So now if we do this, we'll see. So originally the output, so the output of the second layer and the activation are both 64 by 256. So now it should give us like 64 by 10. Okay. So this linear basically maps the last dimension of this tensor from whatever this number is to 10. Okay. So now the last thing we do, let me see if I want to do.
Excuse me, why didn't we directly change to 10? Like first go to 25, 6, and then 10?
Which one?
I mean, like.
Oh, okay. So why don't we do 784 directly to 10? Is that your question? Yeah, we can do that. Yeah, we can do that. But it's much worse than this. So yeah, this can be taught in the numerical analysis class. So a neural network has something called the universal approximation property. And to get the universal approximation property, we have to have, before linear transformation, we have to have a non-linear function like this. Okay, so to achieve universal approximation property. Yeah, that's a very good question. That's an extremely good question. Okay, so yeah, so to get the universal approximation property, we have to do this. So it's like, so for a linear function, so for example, linear regression only deals with simple decision boundary. For example, I don't know if any of you guys learn statistics, but in simple Gaussian mixture model, so most complicated one, okay, so Gaussian mixture, your decision boundary is like circles, okay? The decision boundary is circles and, different circles. But neural networks, the decision boundary can be whatever. And linear regression, the decision boundary is a line. Okay, so so for example, in the classification problem, what happens is if our result is greater than 0, then we classify it to one class. And let's suppose we have two classes. And if it's less than 0, we classify it to another class. So the decision boundary is a line in this case. But neural network, if we add this nonlinearity, the decision boundary can be pretty complicated, and somehow it generalizes pretty well. I mean, this is how your phone can tell, whose face is in the picture. But anyway, so I mean, but this is the key. So in between two different linear transformations, the nonlinearity is the key. So sometimes we apply this softmax function. So this doesn't have to be implemented. So let's skip this, but let's still run this. And so what happens with this output probability is if we look at each row. So for example, let's do 3 rows. Okay, so it actually gives us a probability distribution. Okay. If we compute the sum of each row, we'll get it's 1. Okay. So if it's a probability, this is in the first class, second class, the probability of this sample is in the third class. Because this is random initialization, so it's close to 0.1, means it's equally likely to be in any class. Okay. So this is a probability. And oh, by the way, we see this graph function here, okay? So directly handling this graph function, the variable with the graph function is very dangerous, okay? So let's try to do this. So for example, the output, this will give us this as well, okay? But if we do detach is, we remove its dependence and it becomes an independent variable. So it doesn't have gradient, okay? So this variable doesn't have gradient. Same here, okay? So now if we try to initialize our model, okay, so the input size is 28 by 28. So if we do this, so sample 0 is 64, 64 one channel, 28, and 28 is shared tensor. So the output size should give us 64 by 10, okay? So let's see if it gives us the same thing. Yeah, so this guy is 64 by 10. Okay, so now let's learn the optimizer. So this is adapted from this code. So this code is pretty complicated. So if we go into it. So as we can see, it's quite long. So for example, it has use graph for differentiable. So the step function, this is called a decorator, but we will skip it. Okay. So it's kind of long. So this is like the full implementation. Okay. So this long, but we don't have to learn some. So I simplify it for like the core component. Okay. So this is a class, and this class is the subclass of this optimizer class. Okay. And now this is the same. So this is the same constructor. So this is the same constructor that we initialize this class. And similar to the neural network, so similar to the neural network, so similar to the forward function in NM module, okay? So for optimizer, so we have to implement step for optimizer class, okay? We can ignore this for now, but when we implement quasi-Newton, so this will be extremely helpful, but let's ignore it for now. So, but this is the whole code. So we'll first explain the constructor. Okay. So first is the constructor. So let me remove this typing. So just to make things confused. Okay. So there is another nice thing about Python versus MATLAB. So I think MATLAB added this support in 2023 beta. That is in the function definition. So in the function, this is a function, okay, constructor function. So in the function definition, we can set default value of variables. So we don't have to specify values for this variable again. For example, this is a parameter, but this is fixed. This is like the model parameters. We have to So this is like, we don't touch this. This is like a template. And now the LR's learning rate is basically our step size. Okay, so let me remove this. So this is our step size. So the default value, the default value is 10 to the negative third power. Okay. And when we initialize this class, we don't have to specify this thing. And then when we define, we can use this 10 to the negative third, without defining it. Okay. So for example, so right now, what we do is we do this, and then we do this. So this is basically we initialize this class with this parent class. Okay, so this line of code is we initialize this class using its parent class with these as the parameters. Okay. So, for example, if we run this, okay, and we run this, okay. So the optimizer will have a default class. So we have this, and it also has this LR. So let's try right here. So optimizer parameter groups. Does it have? Yeah, right here. Okay. So for example, it has this LR. It's not, oh, wait, no. Oh, it's not that. Okay, oh, I see. It's params. Okay, so first is params. Parameter containing. Okay, never mind. Tensor, okay. So yeah. Okay. So for example, so what we can try is for group in print type group. So there are like so for example, this syntax gives us the group of everything. So it's a class named dictionary. So okay. So this is why we want to introduce dictionary. So there are two ways to initialize dictionary. The first way is this syntax. Okay. So we can initialize it. We can add more entries. So for example, we can add something more. So for example, method. Let's call, I don't know, CG. Okay. And we can even use whatever, so we can have 0, 2. So how to access dictionary is the first. This is called key. Okay. So for example, dict1 keys. So it gives us the keys. Okay, so LR name method and 0. Okay. So what happens is we can retrieve the items. So for example, we have also this items. So we can needs an argument. Okay. But we can retrieve the items. So let me not do this. So we can retrieve the items by the keys. So for example. So if we have LR, it gives us a value of right here. Okay. So this is a dictionary, and so everything. So in Python, so we like to use dictionary to store the parameters and hyperparameters. So for example, the parameters of a neural network, okay? So the parameter is stored in these three linear transformations in this neural network. So it's stored as a dictionary. So in PyTorch, it's called a state dictionary. And in this is stored in the dictionary. So for example, we can change. So if we want to change this to 10 to the negative second power, okay, we can do that. And if we don't put this is fine as well. Okay. So we have this is 10 to the second power. And but anyway, but if we add one more, okay. So if we add one more, if we add this, okay, we can change the value of the default value. And if we do this, we'll see the value changes. Okay. Anyway, so this is how we define an optimizer. So now let's read this step function. So we can ignore this part. So if closure is not known, this thing, okay. So the loss function is a user-defined function, and this is a huge template, and the return loss is also a template. So what we can implement is this part. Okay. So okay. So these two lines. So for example, this is basically retrieving. So this is retrieving. So this is retrieving the gradient. And this line is basically, so this line is basically the theta, which is a parameter, okay, equals theta subtract alpha, which is our step size, times the grad of f of theta. Okay? So this is the simplest possible fixed step size gradient. So this grad parameter retrieves the gradient, which is f of theta. Okay? So this group, LR, so this is our learning rate, or say step size. And this minus equal is basically this. Okay? But it's an in-place operation that saves some memory. So this is how we implement the simplest possible gradient descent method. So now let's look at our template. So we have this template. Okay, so we have a loss function. So this is called the cross entropy loss. And if it's a classification problem, we can just call this loss function. And this is an optimizer. Oh, I see. Okay, never mind. So I should have I should have reinitialized the model. Yeah, because there is already some backward going on. I shouldn't do this. Okay. Let's add one more. Okay, let's add one more here. So it's a good to do something like this. Why it's not? I don't have empty cache function. Come on. Do I have this function? Let's try it. Oh, it doesn't have. I have to call CUDA. So, okay, so this is a model, and we initialize it, and then the optimizer, the first input is always. So this is template. So the first input, the first input of optimizer is unchanged. So we shouldn't change this. Okay. So this is always this, and these parameters are up to us to define. Okay. Okay. So once we do that, we can run this training template. Again, this is a template you can copy and paste for your convenience. So for example, the first line is, so this is also tradition. So for example, for epoch and epochs, and we do train, and this basically, this is also formality. So what happens is we record the loss function basically is a cross entropy's value in each epoch. So this TQDM is basically a progress bar we learned last time, and this is also, so we can remove this if we don't want to use this. And this is for X target in train loader. So what happens is, so each item, so each iteration in train loader gives a list of XY, where X is like a 64, 1, 28, 28 tensor. Okay, like 64 images, and Y is just 64 tensor. Okay. So basically, this is the image, this is the label, and now we do forward pass, and we evaluate the loss function. So this is our forward pass. So output is our model's prediction. So output is the model's prediction, and then we compare the model prediction with our target, okay, using this loss function. So basically, the output has 10 numbers, and the biggest number, so has 10 each, and the biggest number, this loss function will give us like so if the second number is the biggest, then the output will tell us, okay, so the probability of this in the second class is the biggest. So then so this is optional. Okay, so we record loss function value. So this is optional. This is not essential. And this is essential. So we have to clear the gradient from last iteration. So we don't want our gradient to accumulate, because by default it's plus. So we want to clear it to 0, okay, from last iteration. And then we do back propagation. So back propagation is chain rule. So basically chain rule to compute gradient. And once we do that, we can call this function step function, okay, which is right here. So this is basically gradient descent. And we call the step function, we can check accuracy. This is optional as well. So this is update TQDM. This is optional as well. Okay. So if we want to check accuracy, so yeah, that's not, but let me just add code here, but this is optional. So you can try. So the accuracy. So basically, if we want to check accuracy, basically what happens is we create an array if it agrees with our prediction. So for example, here, okay, then we say, oh, the accuracy is 1. If it's not, it's 0. So what happens is our output has so this is our output. So first we want to detach it. Okay, so it's a long line of code. So first we want to detach it, and then we want to compute its argmax, dim -1. So this gives us this. and then equal targets. Okay. So it's for you guys to decipher my code here, but let me just write one line. And then, so this is how we compute accuracy. And so let's run this cell code. So as we can see, so well basically so this is a progress bar, okay? So the progress bar gives us a bar that we can visualize the loss. Because we haven't enabled GPU, so this is pretty slow. But I mean, normally with GPU, this should be completed with a blink of an eye. I mean, for this small neural network. Yeah. But basically, this is a template. Okay. Yeah. Let me just stop. So basically, this is the template, and that's it for today. So our homework will be based on this template. Okay. So let me upload this.
কি বাসায়
না
কোথায়
75 পোস্টেল
হ্যাঁ
75 পোস্টেল পোস্টাল কোডে পোস্ট অফিস বেশি তো লাগবে না বাসা ভাড়া কিভাবে দাও
হ্যাঁ
তোমরা বাসা ভাড়া কিভাবে দাও
আমরা এই অ্যাপে দিই
অ্যাপে মানে কিসে দেবে
অ্যাপ আছে
রেড হাউস রেড
হ্যাঁ
ওটা থেকে আমি দেওয়া যাবে আমার আইডি নাই আর দেরি করেছিলাম তো
আমার আইডি হয়ে গেছে রাব্বি ভাই তৈরি করে দিছিল রাব্বি ভাই তৈরি করে দিছিল